All right, so if you haven't fired up Jupyter Notebook in a while, then open your Anaconda command line if you're in Windows, or go to Terminal if you're on Mac, and then type in the command Jupyter Notebook and hit enter. Your browser should fire up and drop you off on localhost with your folders. Here, you want to navigate to the ML projects folder that you've set up earlier. And there, you want to create a new Python 3 notebook. And we're going to click up here where it says Untitled, and we're going to rename it to 03 Gradient. Oh man, I can't type. Gradient Descent. And we're going to hit rename. And now we're ready to go. For our first cell in our new notebook, we're not going to be typing any Python code. Instead, we're going to be making our notebook a little bit more pretty, a little bit more readable by inserting a heading. So what I'm going to do is I'm going to go to Cell and then change the cell type from code to Markdown. So select Markdown here, and you'll notice that the IN here has disappeared because this cell will now no longer be evaluated as code. So we said we're going to make a title. Our first title is going to be Notebook Imports and Packages. Yeah? And I'm going to hit Shift Enter. So now we can see here, this is just plain text. And in the cell below, we're going to be adding our import statements. So the first thing that we're going to import is our old friend matplotlib pyplot. We're going to be doing some plotting in this notebook. So I'm going to write import matplotlib.pyplot as plt. I'm going to stick with the same naming convention here. And we're also going to import another library, another package called NumPy. And this is commonly referred to as NP. So a lot of people use NP, and we'll use that as well. So we're going to import NumPy as NP, and we're also going to add the good old Jupyter Notebook statement, %, matplotlib inline. So we're going to be doing some plotting, so we're going to add this matplotlib inline statement so that we can export our plots very, very nicely. I'm going to hit Shift Enter now. And before we go on, I'm going to revert back to this Markdown up here. I'd really like to have a section heading. And let me show you how we can get that, because Notebook Imports and Packages is very, very small. If we put a hashtag in front of this and hit space, then immediately the font becomes a lot bigger, bolder, and blue. And this is because this hashtag is telling Jupyter that now Notebook Imports and Packages should be considered as a heading. Now it's not actually going to look like this when I hit Shift Enter. It's going to look like this. It's going to be big and bold. So this is a very nice way to create section headings in your notebook. Now, if you wanted this a little smaller and one level down in the size and boldness, then you can put 2 hashtags, and you can see how the Markdown adjusts really nicely, and it will look like this in contrast, right? And you can even try 3, right? So there's different levels of boldness and size that you can play with for your section headings to keep your notebook organized. So I'm going to go with 1, and this way we can find our imports very, very quickly. Now we're going to dive straight into our first example. Now the thing I'm going to do though is I'm going to take this cell here and I'm going to modify it to be a Markdown cell as well. So this is my chance to show you a little bit about what Jupyter Notebook can do. So I'm going to say example 1, and example 1 is going to be about a very, very, very simple cost function. And the cost function is going to look like this. It's going to be f of x is equal to x squared plus x plus 1. So let's see what this markdown would actually look like. It would look something like this. But the cool thing about markdown is that you can actually make the mathematical notation look a lot better. So you can add a $sign in the front, and you can add a $sign in the back. And if I press Shift Enter now, then you can see that indeed we have this formatting here in the markdown cell looking like an actual equation. So this is going to be example 1. It's going to look like this. I can make this bigger as well. So I can give it a section heading, if you will. And now it's going to look like this. So this is going to be a simple cost function, right? Here we go. Now, if this is the first time that you're seeing this, then you might be confused about what are these dollar symbols, right? Well, this is a markup notation from a system called LaTeX. And LaTeX uses tags like these $signs to mark a particular section as a mathematical notation. If I double up on the $signs, then I'm giving it a different kind of tag, and you can see that it'll have a different formatting as well. So in this case, it's centered. So single $sign is inline, and the other tag, the double $sign, is for display. So we're going to be using LaTeX a little more in this module, and you might actually see this in many other places as well. It's super popular for writing mathematical equations or scientific papers, especially in academia. The best analogy that I can think of how LaTeX works is that it works really similar to XML or HTML. So if you were to go to a website like, say, example.com, and you right-click on it and you go to View Page Source, then you'll see the HTML document. So while the website will look like this, example domain is actually surrounded by 2 HTML tags, title and title. So a beginning tag and an end tag. And LaTeX sort of works a bit like this as well. You've got markup, meaning these tags, that kind of give structure to your document. So it's through these tags that the Jupyter Notebook knows how to format a particular section of text in the markup cells. Now that we've added the markup and our section heading, we can now actually, write the Python code for this function, and it would look like this: df space f parentheses x semicolon new line return x double multiplication sign for the power, so times 2 plus x plus 1. And that's our function, right? This is our function in Python code. Now what we're going to do is we're going to generate the data. So I'm going to just add a little comment here, make data. And the way we're going to do this is by using NumPy. So our data is going to sit in a variable. I'm going to call it x_1. I'm going to call it _1 because this is our first example. So x_1 is going to be equal to something, and it's going to get its value from a NumPy function. NumPy was NP, and the function we're going to call is linspace. Yeah, np.linspace parentheses start is going to equal -3, comma stop is going to equal 3, and then num is going to equal, say, 100. Let me hit Shift Enter and explain what I did just there. So the linspace function is something that comes from the NumPy library. I'm going to pull up the documentation for you guys. And I've got a couple of arguments that I gave it. I gave it a start value, a stop value, and a value for this third one called num. Now, linspace creates a sequence, a sequence of numbers. It creates our data for us, and it creates a sequence of numbers between the start value and the stop value, and the number of samples is set by that third parameter. So that third value, the NUM value. Back in our Python notebook, we can actually take a look at what this would look like. So if I put x_1 here and hit Shift Enter, then we can see what it is that we've actually got back. We've got back an array that starts at -3 and goes to 3 and has 100 individual data points, 100 individual values that are spaced out equally between -3 and 3. If this, was, I don't know, the number 10 instead of 100, then I'd get an array with much fewer values, right? Just 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So you can see this linspace function here is very, very handy for generating data. And one of the things I quite like doing is actually adding the names for the arguments when I make a call to my function, because I just find it so much more readable than having it like -3, 3, and 10, right? Like that's much harder to read, especially when you're coming back to it and you might not remember it so well. So x_1 is an array with approximately 100 values. We can even give it more. We can even give it like, say, 500, right? I'm going to hit Shift Enter, and that's us having made our data. Now that we've got our data, let's plot it, right? Let's graph it using our function. So I'm going to add the plot by using our matplotlib plt. So we can actually do this in one line, right? We can say plt.plot, and then parentheses, x_1, comma, and then what? f of x. No, f of x_1. We're going to feed the actual data that we have in x1 into our function here. And we're going to plot f of x as this this is our y, right? And x_1, this is our x. So now let's call plt.show, parentheses at the end. See what happens. And here it is. This is what our function actually looks like. It's a parabola. I'm going to actually center this a little bit as well. So I'm going to set the axes by writing plt.xlim, parentheses, and I'm going to give it a range of -3 to, I don't know, 3, right? This is what we generated our data from, right? From -3 to 3. And the y-axis we can set with plt.ylim, parentheses 0, comma, I don't know, say from 0 to 8. See what we get. This is starting to look a little bit better. I'm going to add 2 labels as well with plt.xlabel, parentheses, and then the string x. Give it a font size of 16. And for the y-axis, we're going to just write f of x, so plt.ylabel, parentheses, and then I'm going to give it a string f of x, comma, font size, my typing, font size is also equal to 16. There we go. All right, so that's the plot of our function. So that's pretty good, right? So we've got a cost function, an example of one, x² plus x plus 1. And the way we've kind of broken this down is we've created a function, a Python function, right? Also called it f of x, less confusing. We've created some data, and the reason we had to do this was so that we could generate a nice graph, right? So x_1 used NumPy's linspace, and then we've just used matplotlib again to graph our data here. In the next lesson, we're gonna set the stage for minimizing our cost. If f of x is our cost, then the lowest cost will be at the bottom of this graph, right? So it'll be somewhere around here. All we have to do now is find out what's the lowest cost and for what value of x is our cost the lowest.